Hey guys, welcome to our units digit exploration. So we're going to be going through some interesting problems involving units digits, and these are really aimed to help you get faster at competition problems of this type. Your teacher hands you the following multiple choice questions, gives you 1 minute to complete all three without a calculator. Okay, can you find a way to solve each without actually knowing the answer? So, hopefully you pause the video. If you haven't paused it, pause it and try these out. So one trick, as the title of this hints, is units digit. So if you're multiplying these two numbers, you're going to have to do the 7 times the 4. 7 times 4 is going to be 28, and you're going to carry the 2. The only thing that has an 8 in the units digit is the first answer. Because remember, when you multiply, you're going to have the placeholder zeros, right? So the only thing in that first column is the first product. So same thing here. If I'm squaring the 6, that's going to be a 36, so I'm going to have a 6 carry the 3. Which of these is a perfect square? This one's kind of an interesting one. If you go through your perfect squares, right, so 1, 4, 9, 16, 25, 36, 49, so that's 7, 8 squared is 64, 9 squared is 81, 100. So if you look at the units digits on this, your units digits are 1, 4, 9, 6, 5, 0, and it looks like that's all here. So notice, if I'm asking you which one is a perfect squares don't end in 2's or 3's, so I would choose A as my answer. Okay. So these are kind of interesting problems. Something involving competition problems is looking for time savers. So these definitely would be examples where if you are seeing that pattern, or you're doing the multiplication just focusing on the units digit, right, you're saving yourself time because you don't need to do the full multiplication problem. So here are some trickier examples. Go ahead and pause the video and try and do these two on your own, unpause when you're ready to chat. So both of these were kind of going off of number 3. These are kind of a chunk that go together. And the first one, your units digits cannot be a 2, 3, or a 7, or an 8, just based on the patterns that we saw. If you continued looking at other perfect squares, you would see this as well. And something to think about is when you're squaring something, right? Think about your units digit, right? You would do like 1 times 1, 2 times 2, 3 times 3, 4 times 4. You know, these are kind of like all your digits that you could be multiplying together, right? 10 times 10 would be going one step further. So you really want to stop at 9 because that could be your units digits that you're squaring. And notice none of them, as you go through just your integers 1 through 9, none of them end in a 2 according to our pattern. And so this kind of captures any perfect square's units digit will be 0, 1, 4, 5, 6, or 9. The other digits cannot come, and that's because when you're squaring things, you won't be able to get the 2, the 3, the 7, or the 8. So really interesting pattern there. Some more units digit exploration. At first, it may seem impossible to know the units digit of 1079 to the 87th power. And anytime that you see a problem like this in a competition, there's generally a pattern to look for. So we want to see a pattern, just like the perfect squares. So one strategy, if we think back to, you guys remember that fence post problem where we, figured out how many fence posts were along the property. Remember I told you that I made an easier version of the problem where your distances were shorter so that we could see the general pattern and apply it to a more complex problem. That's kind of like this. We're looking for a pattern, so we want to think simple examples before we go on to a really hard one. So if I do it to the first power, the last digit, the units digit is 9. To the second power, I would have 9 times 9, right, which is 81, so the 1 would be my units digit, and I would carry the 8. If I cube it, 9 times 9 times 9, that's going to be 729. So it ends in a 9. If I do it to the 4th power, you'll get a 1. If I do it to the 87th power, that's what we want to think about the pattern. So right now our pattern is that it goes 9, 1, 9, 1. And if you notice the pattern, every time I have a 9, that's coming from an odd power. Every time I have a 1, that's coming from an even power. So since my 87 is odd, I would say it's a 9. Okay? So just looking for a general pattern as you consider simpler cases. Okay? So for these ones, I want you to put these into your calculator to figure out, each of them as a decimal. At the beginning, you should be able to do some of those on your own, but as you go further, you might not be able to do as many without the help of a calculator. So this is all under the goal of figuring out whether a fraction is repeating or terminating. And there's a nice pattern that we're going to see for knowing which one there is. Okay, so first use your calculator, fill it in, and try and note the pattern of how you know if it's going to terminate, which means stop, or if it's going to be a repeating decimal. So I've done my calculations. I'm realizing now that this was supposed to be on the next page of your course packet. It's not supposed to be, right there on the bottom. Apologies that I ruined the secret. The secret is that the pattern is that the decimal expansion of a fraction in simplest form terminates only if the denominator has no prime factors other than 2 or 5. So you'll notice that the 3 I highlighted terminate. You have 2's here, 5 there, right? If you have things other than 2 or 5, like a 3, a 6, you're going to be in the repeating decimal category. And then these guys are interesting in that there's a pattern for both of them. You're probably noticing that the bottom one is really the same group of digits on a continuous loop. So it was like 2, 8, 5, 7, 1, 4, right? If you started with a 5, like over here, notice it just kind of wraps around. So it's those same digits repeating, and we're just starting at a different spot in the pattern, which is kind of cool. Notice for your 9s, if you have 1 9 on the bottom, it's the number on top, 1 digit repeating. If you have 2 numbers, it's the 2 numbers on top repeating. If you have 3 numbers, it's 3 numbers on top. For something like this one, where I only have 1 digit even though it's 3 things repeating, I can call 2 0 0 2 if I really want, or 0 7 1 for the next one, to kind of see 3 digits, and that's how you obtain the pattern for those as well. So kind of cool. Okay. So figure out which of the following can be represented by terminating decimals before checking the answer with a calculator. So using that general rule that we saw on the last page, go ahead and pause the video, work through, unpause to check your answers. Okay, so there are your answers. Notice we're just looking if we only have 2 and 5 being the prime factors that make up the denominators. So what I've done is I've done my factor trees down below just to show you what they look like, and I've generally just circled if I find a number that is not allowed. Okay? So the 99 pattern, the 9ths pattern, we talked a little about this like a moment ago. So here are some examples with the 9s, right? I do want to point out that we can apply these to things like 11 and 33 if we adjust the fraction by multiplying by 9 and 9 on the top and bottom to make a 99 for the first one, and for the second one we need to multiply by a 3 and a 3 in order to get the 99 on the bottom. And I've already kind of talked through what the repeating pattern is here. So what I want you to do is I want you guys to try those 3 examples at the bottom using the pattern that we already saw. So go ahead and pause, unpause when you're ready to check. Okay, there are your answers. Notice I had to put a 0 as a placeholder in front if they didn't have the same amount of digits as the denominator. Okay, so converting a repeating decimal into a fraction. And this is just like a little bit of practice being familiar with decimals and fractions, just so that you've got that as a skill set. This is useful because this is something that you could do without a calculator, right? So if I have something like 0.5 repeating, I'm going to call x the 0.5 repeating. If I do 10x, right, that's like 10 times x is equal to 0.5 repeating times 10. What happens is, remember, if you do times 10, the decimal moves 1 point to the right. So your 0.5 repeating has moved 1 spot over, and it has become 5.5 repeating. And that's probably the biggest part here, is how we achieve that line of work. From here, if I take equation 1 and subtract equation 2, right, if I'm doing minus x minus 0.5 repeating, you get to the point where your equation is now that 9x is equal to 5, and you have x is 5/9. Okay. This is also something that you can probably just see using the pattern, but this is an algebraic method in order to achieve that for less familiar examples, perhaps. Okay, so here's a practice problem for you guys to do. And then after this, this is the end of the notes. So we will move on to our last topic of modular arithmetic after this practice problem. Okay, so there is our worked out answer. You'll notice that this one's a little bit different from the previous problem in that the last problem we did times 10. Notice the reason we did times 10 was to get something on the other side of the equal sign, right? And we still had the 0.5 repeating. This one we wanted to do times 100 because if I do 100 times 0.24, it moves over 2 decimal places, and I have the 24.24 repeating. We want to make sure the thing that's repeating is the same thing. If I did 0.24 repeating times 10, that would be 2.42 repeating, and it wouldn't be the exact same thing repeating. And you have to achieve that because when we do our subtraction up here, as well as the subtraction here, the repeating decimals cancel each other out. So that's the one caveat, which is a little trickier here, to be aware of how we might adjust and do small tweaks to be more specific to the problem we're doing. Okay, so that's the end of our units digit exploration. Your next video is going to be a topic of modular arithmetic. This is your last one to get ready for tomorrow. And the page number is 174 on your course packet. Okay, so I'll see you guys in the last video.